I just don't remember exactly like what the concept is.
So, in general, when we're talking about a logarithm, they always have a base. The base has to be a positive number other than 1. When else have we seen a base with a positive number other than 1? Exponential. So, exponential and a log are closely related. Is another way of writing an exponential equation. So, y equals log base a of x means x is equal to a to the y power. Just like with, well, I'll let you write that and then I'll talk. Okay, so we can go back and forth between exponentials and logs. The base of the log, the base of the log is the same as the base of the exponential. Okay, and it always just goes cross equal signs. So it's a to the y power is equal to x. Okay, or if you were writing this as a log, it'd be log base a of x equals y. So a logarithm is essentially telling you the exponent. When I see log base a of x, it's like telling me what exponent of a would make it equal x. So we're looking for that missing exponent. So we can go back and forth between the two. The base has to be a positive number other than 1 for both an exponential and a log. We also know that if you take a positive number to a power, you get a positive answer, right? So the argument of a log has to be greater than 0. Right? And we saw that with when we were graphing exponentials. We had a horizontal asymptote at 0 and we didn't hit anything below that. So that will be our domain. So first thing, we're just going to practice going back and forth between the two. So if this one is an exponential, if I asked you to write it as a log, so we have log, the base is a subscript. So it is a small number written below the log here. So what is the base of my log? The same as the base of the exponential. So it's log base 1.2 of m, and it equals the exponent. So it's equal to 3. So B, if I ask for this written as an exponential, the base of the exponential is the same as the base of your log. So we would start with the base of e to the negative third power equals b. All right, you guys do C and D. So how did you write C? 3 to the c power equals 5. And D would be? All right, are we good with those? So we should know how to go back and forth between the two. Now let's start evaluating some logs. You have a log button on your calculator. However, that button is log base 10. There is a way on the graphing calculators to get to other bases, but it's not the easy or not super convenient. But really, we need to be able to evaluate these without a calculator because you know that ultimately we're going to start having problems with variables in them, right? So we don't just want to plug things in the calculator, we want to think about what it means. So there's two options. Option number 1, if you understand what a log means, you might be able to look at this and tell me the answer. Log base 2 of 16. It's saying 2 to what power would equal 16? 4. So if you can look at that and understand what it means, that's great. If not, set it equal to x and change it to exponential form. So you start with the base, so it would be 2 to the x power equals 16. Didn't we solve problems like this on our last test? Common base. So 16 is 2 to the 4th, and x equals 4. So if you get stuck, you might have to write it out and solve it like an exponential, or you might be able to just look at it and know. So when I see B, log base 3 of 1 over 27, that means 3 to what power would equal 1 over 27? To flip it to the bottom, we know it's a negative, and 3 to the third is 27. C. Log base 2 of 1 means 2 to what power would equal 1?
0.
And D. Log base 5 of 25 means 5 to what power equals 25? Alright, does everyone understand how we evaluated those? So, if we are evaluating a log, you can change it to exponential form if you need to, or if you just talk your way through it, you'll be able to get there. Now, when I start throwing variables in, then we're going to have to probably write it out into exponential form. So let's take a look at that. So if I asked you to solve this, alright, it's not one where I can just look and know the answer. However, if I change this to exponential form, what would we write?
3 squared is equal to 4, that's
3 squared is the same thing as 9. So head over a 7, divide by 4, and get x equals 4. We do have to check on these. What we're really checking is with a log, both the base and the argument have to be positive numbers. So you need to make sure that when you plug in your x, you're not giving a negative base or a negative argument. If I put in 4, 16 minus 7 is positive, so we're good. Okay, if it gave me a negative, then it would be a no solution. B. X squared, x log base x of 64 equals 2. So if I write that as an exponential, what would I write? Yep, the same thing I started to say. How do you get rid of a square? When you add a square root, what else do you need? So we get positive and negative 8. Now we check. If I put in a positive 8, am I okay? Can I make that base a negative 8? No, because definition of a log, the argument has to be positive. So 8 is the only answer that works. Why don't you guys try a couple? So this will give us x to the negative 2 equals 16 over 9. Different options. What'd you guys do? Okay. Then what? You square rooted each side. So we could do that. If you square root, you have to do plus and minus with it. So you would have 1 over x equals plus or minus 4/3. Then what do you do? There's different options. Could we just add an exponent to each side once we do the same exponent to both? There's different options. We could like cross multiply here and solve, or you can flip both sides. So 1 over x would just be x equals plus or minus 4 over thirds. If you flip that, you get 3 over 4. Is that how you guys got, or did you get that answer? There's a lot of different ways. Okay. The base has to be negative, or has to be positive. Now, that doesn't just mean that x can never equal a negative number, because in my original problem, if my base had been like negative x, then you would need the negative. So you do need to check them. But when we plug it back in, the 3/4 is the only option. All right, B. So 16 to the 3/4 equals x. 3/4 means the 4th root of 16 cubed. 4th root of 16 is 2, 2 to the 3rd is 8. And is that answer okay? One more. You guys didn't have this one to do on your own, but let's see if we can figure this out. So if I work out this one, we get 36 to the x power equals the square root of 6. What would you have to do here?
So some of those is
Okay.
6 to the 1/2 and 6 squared.
Okay, 36 is 6 squared. The square root is a 1/2. So 6 to the 2x equals 6 to the 1/2. That right here, so x is 1/4. And does it matter if it's equal to a positive or negative number? No, it's just the base and the argument that have to be positive. All right. Do we need any more problems like this?
You said the argument is what's next to log.
Mhm.
So those both have to be positive.
Yes, but what it's equal to can be negative, because it's equal to like the exponent, and we can have positive or negative exponents. Alright. Yes. Second thing I wanted to mention, the buttons on our calculators. So for now, you're only allowed to use the log and the ln button. Okay? We're not going into our menu and getting any different bases yet. With this, that log button is log base 10. The ln is a log base e. But if I ask you to evaluate, it's pretty simple. You just push that button, type in my 46. So the log of 46 is 1.662 and I asked you to just evaluate this, so just straight from a calculator. The ln, a lot of times when we have that, it has an e with it. So if you do the ln button, it opens a parenthesis 8 times. And to get the e, if you do second ln, it does your e for you. And you do your e to the 6th. And that one gives
Is
me,
that x multiply?
yes.
Okay.
Sorry. A lot of times we see those in scientific notation and things, so you'll see the x typed out as a multiplication sign. The last piece that we are going to add in today is some properties of logs. We're going to do a little bit with it, and then we'll pick up there tomorrow. Does everybody know how to plug these in your calculator? So the first slide, I'm just going to have you guys write this stuff down, and then I'll talk about it. So all these stipulations, I have the domain x, y, and a all have to be greater than 0 because those are used as bases or arguments. A can't be 1, but R could be anything. So the product property says if you have a log of 2 things being multiplied, then it's the same as adding their individual logs together. Okay, and it's all very closely related to exponentials. You know, if I have 2 to the third times 2 to the fourth, what do you do with those exponents? You add them. And it would give us 2 to the 7th. Okay, so this idea is these things represent the exponents. So if you have those being multiplied, when we break them apart, we add the exponents together. Quotient property, if things are being divided, then you subtract the logs, just like if I said 2 to the fourth divided by 2 to the third. What do you do with your exponents? You subtract them. So the power property says if you have the log of something to a power, that power can turn into the coefficient. Okay, because this log is representing an exponent here. So exponents come down in front of the logs. The other two things are just results that you don't necessarily have to memorize. It's things we kind of know. Log base a of 1 equals 0. It's saying a to what power equals 1? Well, anything to the 0 power equals 1. And if the base and the argument are the same, it equals 1, because if I said log base 2 of 2, it's saying 2 to what power equals 2? The first power. Log base 3 of 3. So those are not necessarily rules you have to memorize. It's just kind of things that we know as we think through the logs. The second slide here, I have 2 more properties. They're related to the fact that an exponential and a log are but they're inverses of each other. They undo each other because the log is helping us find a missing exponent. So if you have the base of the exponential and the base of the log, if they are the same, they essentially cancel each other out. And I can give you some justifications for this. If I said like 5 to the log base 5 of 7 power. And I asked you to solve that. Okay, this is written as an exponential. So if you wanted to change it to a log, you would say log base 5 of x equals the exponent, which is log base 5 of 7. So then we could see they're both log base 5, so the x has to be 7. This one, we could really use that property that if you have logs with it, that exponent can come down in front. So log base a of a to what power equals a, that's just 1. So that gives us r. So if you have an exponential and the log with the same base, they essentially just cancel each other out. We're going to do just a few examples of this and then I'm stopping for today. So if I asked you to tell me what each of these things were equal to. The first one. 2 to the log base 2 of pi power. Worst case scenario, you set it equal to x and try to use definition to figure it out. Best case scenario, what do you realize? So the base of the exponential and the base of the log are the same, and I told you that if that happens, they really just cancel, so what would this equal? Pi. So if you recognize the properties, it can save you a lot of work. Otherwise, you would have to set it equal to x, it's an exponential, so change it to a log, so log base 2 of x equals log base 2 of pi, and then we can see that x is equal to pi. B, What's the answer to this one?
Square root -2.
Negative.
Negative square root 2.
Because the log and the exponential are the same base, so they essentially cancel. What's the answer to C? 71, because the log and the exponential have the same base, so they cancel. This is where I'm stopping today. There is a handout posted on Classroom, and we'll pick up working with